Number 1 asks us, for each growth rate, find the associated growth factor. So remember that the growth factor is going to be 1 plus the rate. And if you do it like this, then you need the rate as a decimal. Okay, you can also do 100%. So if you want to do it with percents, you can do it as 100% plus the rate as a percent, and then change this into a decimal. And we change a percent into a decimal by dividing by 100 or moving the decimal back 2 places. So if we're talking about a 30% increase, so we have our initial 100%, plus we have 30% increase. So increase means we're going to be adding that. So our total percent increase is 130%. And then if we divide that by 100, we get the growth factor of 1.3 or 1.30, however you feel like writing that. Number 2 does a 30% decrease. So if we have 100% that we start with and we decrease, meaning we go down 30%, that means that each time period we only have 70% of the remaining. So then we'll do that as a decimal, and that's going to be our growth factor of 0.7, and you can do 0.70 if you want to, it doesn't matter. That would be your growth factor. So then a 2% increase, so that's going to be up 2% from 100, so plus 2%. So then this is 102%, divide by 100, and we get 1.02 as the growth factor. A 2% decrease, so now we're going down 2% from 100, so we'll subtract 2%. So now each time period we only have 98% of what we had before. Divided by 100 gives us a growth factor of 0.98. And remember, anytime it's decreasing, your factor is going to be less than 1. And if it's increasing, it's going to be greater than 1, because that 1 represents your initial 100%. Part E has a 0.4% increase. So this is going to be 100% plus 0.04%. So that means each time period we have 100.04% more. Then when we divide this by 100, we get that the growth factor is 1.0004. Then a 0.04% decrease, we would be subtracting that 0.04% from 100. So that's going to be 0.9996. Oops, not 0. This was the decimal part. So 100 minus 0.04 is 99.96. So then that's the percent that we have each time. So divide that by 100 and we'll be at 0.9996 for our growth factor. And then finally a 100% increase. So we'll have our original 100 and then we'll be going up another 100, which gives us 200% each time. And then divide that by 100 to write it as a decimal, and we get a growth factor of 2, which makes sense, right? It doubles, it takes its initial and gives you back a second amount. Number 2, in 1990, the population of India was about 870.5 million people. By 1995, there were 960.9 million. Here's the equation that approximates the number of people in millions in terms of the years since 1990. By what factor does the number of people grow in 1 year? So we have this in our equation, right? So this is the terms of number of years since 1990. So our growth factor, so once the factor is going to be this, so 1.021. If D is the time in decades, write an equation expressing the number of people in terms of decades. So remember, this initial equation is written in years. So this T is in years. So now we want to think about how many years are in a decade. So if we plug the decade up there, okay, which is 10 years, that's how this is going to change. So the population now is going to be 870.5 times 1.021 to the 10D. Because if we put in 1 decade up here, okay, so if D equals 1, then we want that exponent to equal 10. Because we want there to be 10 years that happened. Okay, so 10 times the number of decades. Use the original model per year to predict the number of people since 2015. Okay, so now we're just going to use that original model and figure out for 2015. So 2015 is 25 years since 1990. So that's what we're going to plug in. So we have 870.5 times 1.021 to the 25, because we have 25 years. And this is going to give us about 1,463.6 million, because remember, this equation is giving it to us in millions. So make sure you write million after that. Then it says in 2015, the population was actually 1,311 million. How does this compare to the predicted? So here's the predicted is 1,463 million versus 1,311 million. So the prediction was, or the actual, how does this compare to the predicted number? So the actual was about 100 million lower. So it over predicted the population, right? The model over predicted the actual population. Number 3, an investor paid $156,000 for a condominium in Texas in 2008. The value of the homes in the neighborhood have been appreciating, mean going up. Okay, they've been increasing in value by 12% annually or each year. Select all the expressions that could be used to calculate the value of the houses in dollars after T years. So I like to just kind of write out my own equation off to the side with how I know how to do it. So then I can start trying to compare to the way that they do it. So I know that if it's increasing by 12%, one way I could do that is by doing 100% plus 12%, which gives me 112% is how much it will be the next year. And then as a decimal, if I divide that by 100, that's a factor of 1.12. So I could, think about it like that. So 1.12 is that growth factor. Another way I could look at that growth factor is looking at 100 as a decimal, 1, plus my percent 12 as a decimal, which is 0.12. So I could get to the 1.12 this way as well, 1 being 100% and 0.12 being 12%. So then let's take a look at these options. So over here, part A just says that we're taking 156,000 times 0.12, which would be wrong. This would actually be depreciating by 88%. Okay, we're only getting back 12% of the value, not 112% of the value. So this one would be bad. B matches the way we wrote the first one. So the growth factor of 1.12. So this is perfect. C is great. 100% plus 12%, just written as decimals. D is acting as if it's depreciating by 12%, and that's not what it said. It said appreciating, increasing. So this one would not be correct. And then E is dividing the rate by 12, which then is looking kind of at doing if it was raising 12% and we were giving it back monthly, but this is not what we want. Okay, we want 12% per year. Number 4, a credit card has a nominal annual interest rate of 18% and the interest is compounded monthly. Okay, and the number of months that there are in a year is 12, so it's being compounded 12 times. The cardholder uses the card to make a purchase of $30. So this is our initial value on the card. Which expression represents the balance of the card after 5 years in dollars, assuming no further charges or payments are made? So we have the original amount, right? The $30 purchase. Then we have this growth factor that we need to figure out. Okay, and this 18% is going to be split up 12 times. So you're going to end up with 1 plus the interest rate as a decimal, which is 0.18, right? So 18% as a decimal, we would divide by 100, and that would give us 0.18. So when we plug it into here, we're working with numbers, not percents. So 0.18 compounded 12 times per year. Okay, so then this is how much you're getting each year. Divide the rate by 12, okay, add it to your previous 100%, calculate that 12 times in a year. Then this problem specifically asks us to do this for 5 years. So then we're going to multiply this because it's 12 times per year. So we're going to do 12 times 5 as the exponent. And then we see that that is option D. Number 5, the expression 1,500 times 1.085 to the third represents an account balance in dollars after 3 years with an initial deposit of 1,500. The account pays 8.5% interest compounded annually for 3 years. Explain how this expression would change if the bank compounded quarterly. So quarterly means 4 times each year. So 4 times per year instead of just 1 time. So we would want to think about that this 1.085 here really came from 1 plus your interest rate of 8.5%, right? So 0.085. So that's how we ended up with that 1.085. And when it's being compounded annually, then you're just dividing it by 1 because you're paying it out 1 time per year. So if we were changing that to paying it out or charging the interest 4 times a year, okay, then we would need to change this interest rate to be divided by 4 and giving it to the customer or the account holder 4 times per year. So this would change that inner part to 1 plus 0.085 divided by 4 and then to the 4th power. The 1,500 would stay the same, right? So we'd still have the 1,500 here because the initial deposit didn't change, just the way they're calculating that interest there. And then we'd still have the times 3 up there. So write a new expression to represent the account balance if interest was compounded quarterly. And that's going to be this expression that I just wrote. So if you wanted to explain how it would change the interest compounding, right? And then that's the new expression. Number 6, the function f defined by f of t equals 1,000 times 1.07 to the t represents the amount of money in a bank account t years after it was opened. how much money was in the account when it was opened. And so the amount of money in this account is $1,000. Number 2 asks us to sketch a graph of F. So you can be, as detailed as you want with this, but it does end up asking us in C when the account reaches $2,000. So we will want to be able to see that. So you can go to Desmos or use a graphing calculator or just plug numbers in and plot points. But here's a sketch. So then it wants us to know or to tell when the account will equal $2,000. So we can just look at 2,000 here, see when it crosses the line, and then go down and find out that that happens after about 10 years. Number 7 gives us it says the graph shows the number of patients with an infectious disease over a period of 15 weeks. Give an example of a domain for which the average rate of change is a good measure of the function. And remember, average rate of change, this is going to be a straight line, constant slope. Whoops. So you want to look for where a straight line would maybe connect points and would still showcase what's happening. So if we look here, like if we said, from 1 to 5 weeks, that's a pretty good indicator, right? That would be 1. Now there's multiple answers to this. Okay, so I could say that my weeks, if they're between like 0 and 5 or 1 and 5, that would be a good indicator. You could say other things, right? So you could say, well, from 4 to 6 appears that the constant rate or the straight line connecting those 2 points looks like the graph. So this could be 4 to 6. You could do 0 to 1. You could do 0 to 2, 0 to 3. Okay. You could even probably do like 0 to 6 looks like maybe it's pretty close. Maybe it's missing a couple there, but it still feels like a pretty good indicator. So lots of different answers you could have there. And then also lots of different answers you could have for this other one where it says that it give a domain that's not a good measure. So not a good measure would be something like this. It misses most of those points. It's growing really slow here from 0 to 5 or 6 weeks. Then it starts to grow significantly faster before it gets here. So 0 to 12 would be an example of a domain that doesn't seem to be appropriate. Okay. Also, you could do, let me leave this one here. But you could do 4 to 14, 4 to 15, 4 to 11. Any of these really are bad for the average rate of change. The average rate of change does not represent that graph in any of these where the straight line misses all of these points. So don't have to use these 2. There's significant other alternative answers. Just make sure that when you connect your numbers that they make sense on the graph. Number 8, a party will have pentagonal tables placed together. The number of people, P, who can sit at tables is a function of the number of tables, N. Part A says, explain why the equation 3n plus 2 defines this function. And so there's some different ways you could say this. But if we look at it, we've got like these 3 people. Okay. There's 3 people at this table. There's 3 people at this table. Then you have this end and this end. Okay. If we looked at this second set, we've got 1, 2, 3 people, 1, 2, 3 people. And then we've got this end and this end. When there's, nothing connected, you still have 1, 2, 3 at this table, and then you have this end and this end. So you could say 3 people can sit at each table. Plus 1 on each end. So each end would mean 2, right? Each end of the group. So you're thinking of this as the each end. So 3 for each table, and then add 2 for the ends. For part B, it says how many tables are needed if 47 people come to the party. So 47 is the people, right? So we have 47 equals 3n plus 2. So if we solve this backwards, what we're doing is we're subtracting 2 to get 45 is our 3n, and then dividing by 3. So we end up with, we need 15 tables. So if we add 2 at the end, if we do 3 times the tables plus 2 to work that backwards, we would be subtracting 2, then dividing by 3 to get to the number of tables. So how many tables are needed if 99 people come? So we would subtract 2, which gives us 97. And then we would divide by 3, which gives us 32.3 repeating. Okay, and you can't have a third of a table. So in this case, we would need 33 tables. And then write the inverse of the function and explain what it means. So we kind of talked about that here. So if you have the number of people, you would subtract 2, and then you would divide by 3. And that's going to be the number of tables needed, because we'll take off the 2 end spots. Okay, so remove the 2 end spots because you'll put people there, and then take the rest of the people divided by 3. That's how many tables you'll need.